boom, boom, two parts. You gotta solve this and then substitute it in there. I think you do that. I think you're going to show that that's the notion that if you actually drop the temperature in the temperature now, that's not plausible, but that's the number.
So if the temperature is down, going down.
Yeah, but see, I kept the temperature exactly the same with all of
Yes.
these.
If I need a situation, the temperature going down, but the carbon dioxide is also going down, that's more.
That's the
And like in the future assignment, I realize I have something wrong in that song. Can I just use the email like this to correct my answer?
We're opening up so you can go do the exam again, up till the time that's due.
But usually I write it on 400 words.
Yeah.
And yeah,
But we're allowing you to go back in and do it again, or to modify.
modify.
We've set it up now so that once you submit it, you can go back to it.
Okay.
Yeah. For the next one, not this one.
I'm not next.
For next time, next tomorrow.
So I can see what I wrote after I submit.
Well, you can see what you have on that till you submit it, till the deadline.
Thanks.
Okay? What time is it going to be? What time? 2. It's 2. And this is a Tuesday, so happy Tuesday. I have what day of the week it is. So this is the third lecture or session on climate sensitivity. We put this away. We keep all of some good information. After today, there's another one more homework. And then we are going to move on to something called droughts, I think, next. But the point is that climate sensitivity is largely that it's some sort of metric or prediction. We've dug into the details of how you can calculate it if you wanted to do such a thing. We've dug into the details of how we did it in the paleo record, or how people have done it in the past. And so we've got some sort of knowledge of that. And that was basically lecture 2. Concept introduced on 1, you got some information. Number 2, we did a little more analysis. Number 3, we're going to think a little bit more about what it all means. So that progression is going to go on the whole term. We're going to go from just simple information gathering to have a few facts, we'll put them together in some way, but the real challenge point or the real knowledge comes from, what are you going to do with that information? Okay? So let's dive into this, which means basically I'll comment on the assignments today. I'll introduce some new topics, one called spheres, the notion that the Earth is a complex place. I'm going to talk specifically about something called sea ice, because it's an example of something of what we call feedbacks. Feedbacks are one of the reasons that this whole problem is not so simple as the algebra that we did. Put it out. We'll talk about water vapor as a important greenhouse gas. We've already said that it was the one that has the most effect. And I like this little saying, but I'm not sure I knew it enough. In science and in most fields of knowledge, there are 2 things of unknowns. There's the known unknowns and then the unknown unknowns. This we know something that there's a problem. We don't understand it. These are things that we haven't conceived of that we don't understand yet. A lot of the things in the climate system actually fall over here. This climate sensitivity falls into here. We know it's not a great thing, but when you start talking about these puppies and this puppy and this, you start delving into this. I can give you a lecture that sounds like it's all perfectly well known. The reality is I can open up a technical paper where they're going to challenge a lot of assumptions about it because it's a big point of debate. So the unknowns are being discovered. And that's a theme I'm going to try to hold forth. By and large, the second exercise was pretty good. We've still got a few rough edges, but we're working them out. Again, it's an exercise in preliminary data gathering. You dug in the information. We did a little math. It's not a very complicated math. We weren't perfect as a group getting the math conveyed to the expression, but you know, if you had to do it again, I think everybody would be fine. Generally, as a side note, we'll talk about temperature C, just because it's a technical class, and the conversion is 5/9 if you have to worry about that. One of the other skills I'd like to develop is sort of a common sense one. Does an answer that you get make sense? It's a lot easier to do once you know something about the exercise. And the more you have experience, the easier it is to do. But it's was that somebody just banging on the door? Hello? You gave up on this? Can't win for losing, right? So the point is that if you do an estimation like this, sit down and kind of think about it. Once you plug in each of the numbers, does it make really sense? In the case that we have now, there was 3 different cases, basically. Should or shouldn't they all give the same number? Well, there's a lot more reasons they shouldn't give the same number than that they should. But are they useful? In our case, we did some calculations, but we talked about climate sensitivity, and we said the values are sort of between here and there. Something like that. So if you're getting 27, then you might, if you would thought about it and gone back and said, well, what are the values that you actually get? And you find your values way off, should raise a flag, and you can think about it. I don't care what discipline you go into or where you go professionally, you're going to want to do this kind of analysis on anything. Whatever I've come up with, does it make sense? And so I'm going to give you a lot of chances to practice that. All right. When we talk about temperature, one of the challenges of this thing is that a lot of graphs that you see talk about temperature, not in an absolute sense, but in an anomaly sense. How does it deviate from something? So everything you see basically is not the absolute temperature of the Earth, but it's a prediction of how different it will be. We'll go back over that, but I just wanted to bring it up here. Those are the general comments that I have, except for the notion I want you to be aware, and I think the sense that we got, Liz and I, from looking at the exercises, that people still a little, maybe too hesitant to ask questions. So please do. The class offers an opportunity to ask questions, and if you don't ask questions, I'm going to ask questions back to you like we did the other day, where we walked through these 3 events and I randomly picked on somebody. I wasn't picking on somebody, I was giving you an opportunity to dialogue with you. So don't be fearful of us. We're here to help you. Second point is, there's no formal posted office hours, but either of us are available basically any time. So we have to know that you want to come to us. When you ask us, we'll respond. So. And the third point I think Liz pointed out to me today is if you're sitting there and you're wondering, why doesn't this make sense? Probably the person sitting next to you has the same question and the person sitting next to them has the same question. So don't feel that you're the only one that's a little bit, that's maybe not getting something. Easily be getting something because I'm not explaining it very well or I'm assuming too much. But again, raise a question. Liz, what did I miss?
Nothing that you missed, but if you don't mind me jumping in real quick, almost all of you, in fact, I think literally all of you are non-majors. So if some of these terms or concepts seem foreign to you, that's okay. This is all supposed to be new information. So please do not feel uncomfortable or nervous about asking basics. It's totally normal. And I literally was in your position last year at this time, in a class just like this. And I promise you would get so much out of it if you just ask the question that you think might be a little uncomfortable. And we don't bite, I swear, we don't bite.
And as Liz points out, I'm not trying to fill you through all the facts on all parts of all climate or all global warming. I'm trying to give you a few examples, and what we're really worried about are examples here. And so we're trying to dabble in a few things to get some ideas across. All right, turn it over to you. Questions on this assignment? Anything that somebody wants to raise or discuss? We had a discussion earlier about how the formula is set up. Something else that anybody wants to ask? Why did I only get a 3 or a 4? Well, yes, ma'am.
Do you give an example on how to do like the calculation for like climate sensitivity?
Can I give an example, or have I? Or
Yeah, like I just haven't seen it like worked out, so like I didn't know like.
okay, so if I can jump back to last week's notes, that's where it's laid out.
Oh, it is, okay.
But let's go through it. It's gonna take me a minute to get to this point. Oh, it happens to be on that page right there. Who would have thunk it? So I called it the back calculation, but here's the climate sensitivity, right? And the general concept is if you double, it's a number, and if you double CO2, how much will the temperature change? It's an arbitrary thing. I could have said 1.6, but doubling sounds more impressive. So it's an empirical relationship. So what we know then is that the temperature changes because it's a time thing. And we know that CO2 changes, and in fact, at the end, it has to be 2 times the beginning amount by definition. So this lays out the underlying principles, right? The next step is to recognize that solving this algebraically, I always get confused about how to do it. I have to redo it every year, but that's okay. So I set up a scaling factor. This is not the only solution. But we set up a scaling factor that depends on how much the CO2 changes. And that's right there. The concentration at the start divided by the concentration at the end versus the minus the concentration at the start. So how much did it change by? So this gives me some sort of scaling factor. So far, so good? Okay. And if it was exactly 2 times the CO2, it all washes to 1. But none of the examples we had come anywhere near exactly 1. So what you do is apply that to the temperature at the end minus the temperature at the start, and that gets us back to this. So the formal equation is this, which 1 or 2 folks bypassed the actual S and stuck this back in here, and it'll work just the same. So now all we have to really get are the numbers at the beginning of the global warming, where with the temperature, and they were low, and the CO2 levels were low. And then after those 3 events, we could get the resulting increase in CO2 and the resulting increase in temperature, and then back calculate to get this right here. It's technically the slope of the line, but let's not worry about the math. Does that explain it a little better?
Yeah.
And then what I did to follow that up was I showed the spreadsheet that I had set up that has a whole different range of exercises. I kept the temperature difference always the same, but I messed around and kept the starting CO2 always the same, and I just messed around with the ending CO2. And therefore I could calculate a really wild one, an improbable one, and then other ones that are sort of realistic. And it's like I used a spreadsheet to check some answers. I stick them back in there, give me the start and stop temperature, I can calculate it. It's just that algebra. That helpful?
Yes, thank you.
Okay, anything else? All right, let's see if I can get back to the other lecture. And this should be climate sensitivity 3. And that's that. Okay, so we did 3 time slices of review, blah, blah, blah. Guess you know all that. The answer was purple. The bonus question was purple. Paleo. It's study of the past. All right, I don't think there's anything new on there. Let's get out of that. New material. The Earth could be considered a series of spheres. It's like an onion. You start with the center of the Earth, and you can work outwards in a whole succession of rocks, and then you eventually get close to the surface of the planet, and you start getting into rocks and liquids. And if you go up in the atmosphere, you get another whole layer of atmosphere things. So if we sliced and diced the Earth in half, you'd get gases down to liquids, down to solids, and you go back up in round numbers. So that's the solid sphere, we call it the hydrosphere, and the atmosphere. Some people would say that there's even more spheres, and that's fine. What I want to emphasize is on all of these layers of things, the sun's energy is at the Earth's, hitting the Earth's surface. Now, the Earth's surface in some places is liquid, in some places it's solid. And then the atmosphere has this little tricky-dicky thing that it does. All right. There is energy in the center of the planet because it's hot and molten. That energy is so small and so constant, it makes no difference to climate change. The sun and the interactions at the outer two spheres, the atmosphere and the ocean, are where it's at. So we can talk about the geosphere being the land, the hydrosphere as being basically the water, and in the hydrosphere we would combine the oceans and fresh waters. And then the biosphere, which is the biota and plants and the living things that make up part of the system that do influence it in some ways, but more respond to it, and that includes us. We're the exception of making something else work. Cryosphere, which is a word you haven't heard probably so much, that's ice that our planet is now. Because we're an ice age world, we have a lot of ice on the planet, so we break up the water into the solid and frozen states because it behaves a little differently in the atmosphere. And so those are the key ones that ultimately, if you were studying the whole climate system, you would end up focusing on one or the other of these things and then seeing how that worked. And professionally, I spend all my time worrying about the cryosphere as an example. All right, let's think about that a little bit differently. All of those things that could be, all of those 4 or 5 things could be represented as a dot, as a sphere of itself. And the real point is that there's energy flow amongst all of them. So the cryosphere gives way to the oceans in some sort of energy and mass transfer. The atmosphere gives way to the oceans. The oceans give way to the cryosphere. That gives way to biology. Whatever you want to put its labels on those. Take-home point is all of those are exchanging energy in all different ways. So far, we've only talked about the energy coming in from the sun, something magically happening in the atmosphere, and then the energy leaving the planet. We want to dig a little deeper into that and not go through all of these verbatim. That would bore you to tears. But we want to be aware of, and so what we've really dealt with is the atmosphere. We'll get to the oceans as a whole separate unit. So far, so good. They all have to be in balance. They all have to be in balance. They're in balance with each other. But because those arrows actually have different physical or chemical mechanisms, there's lag times. So if we can change one thing, and eventually it'll propagate through the system, but it might not be this week. It might be on geological timescales. One example was shoving up the Himalayan mountains. That happened over millions of years. That slowly raised the Tibetan plateau. That changed the atmospheric circulation. It took a few million years for that effects to be felt, and they're still affected today. Same thing with the opening of the continents. On the other hand, cloudy days, there's something called El Nino going on right now. That's an interaction between the ocean and the atmosphere. Happens on a 2 to 3 year cycle. And we always see weather patterns, and so we don't know one day is going to be this warm, and the next day is going to be that warm. Again, the point is that there's some time lags in these things. So sometimes we talk about equilibrium, sometimes we talk about instantaneous, but not instantaneous in this class so much. That gets noisy. One of the interactions I want to highlight for the sake of argument has to do with sea ice. And that's an interaction between the oceans and the cryosphere at some point. I should have put cryosphere on that slide. But sea ice is a solid form of water, And I could diagram that, this cross section. So here's the body of the ocean, diagrammatically. Here's a hunk of ice on it, diagrammatically. Here's the energy coming in yellow for the sun. Now, one of the things that we see here is that there's might be a couple different ways that the energy can interact. I'm not gonna go into those in super detail right now, but a lot of the sun's coming in will bounce back out. But what about the contrast between where the sun is and where the ocean is? That white has a property we call albedo, and I think we'll go back into that later. Basically, it bounces a lot of stuff back off. If you stand on a dark surface that is absorbing energy, then you feel hot. If you stand on a light-colored surface, you feel a little cooler. But the ice basically will bounce things off more than the ocean will. So there's two sunbeams coming in, one hits the ocean, one hits the ice. The ice will throw it off, the ocean will suck it up, some portion of it. And that's because it's darker. Now, so at some level, if I do that, and I'm not sure what this guy, so ignore that arrow, but at some level, it'll come in a second. Let's just assume that I'm warming up that ocean because I'm beaming the sun on it and it's absorbing it. So of course it's warming it. So now I've got an ice cube in here. What's going to happen to my ice cube? It's going to melt. The difference between the solid and liquid phase of water is purely an energy consideration. And water is the really weird thing that actually expands when it gets colder, so it floats. And if it didn't float, we wouldn't have life, but that's as we know it. But that's a different story. But here's ice. It's happy, happy, happy. It's an ice cube in my drink. I pour warm water in, the ice cube melts, goes away. Fine. What's the next step in this? This box was in some kind of balance. The amount of energy coming in, going out, everybody's in balance. That box is in balance. It's in balance with that much ice. If I change that much ice, do I change the balance? Yeah, because I've changed the system somehow. Less area to bounce out directly, more energy to warm this up, right? So that's the sort of the physics under this. Let's see if we can talk then more specifically about sea ice with the polar bear, which is the type section of the northern hemisphere of it. Sea ice, because polar bears are white and that's all kinds of things. You see quite a difference between the different places on that sea ice. You see different colors. These little pools are on top of the ice, and they're melting because, and once they start getting melting, they're going to get bigger and bigger because they get warmer and warmer. This ice over here is not, the polar bear is not going to walk through that. You can swim, he or she can swim through that. And this water is the darker color, and the more energy is absorbed there, but it's a chaotic process. But this is the environment that we're dealing with, the sea ice. Anybody ever see sea ice? Sea ice? Not so much, okay? So, sea ice today, the ocean has a funny property. It's got salt in it. So I can freeze my ice cubes in my refrigerator upstairs some days, on good days, and that's fine. But if I tried salt water in my refrigerator, they're not going to work. The salt makes for a higher temperature or a colder temperature that I need in order to freeze it. So the world's oceans are floating with the sea ice. It's only, the point is, it's only where it's cold in both poles. And we have talked a little bit about it, but the two polar hemispheres, the North and South Pole, are quite different. One of them's got ocean all the way around it, one's got landmass all the way around it. I'll leave it to you to figure out which one is which, but they both have sea ice. And that's because it's cold there. So now let's think about this system a little bit more. Let's start off with an ocean. Let's start off with the ice covering the whole area of concern, and that white stuff, and then there's a vast majority of that energy will get bounced right back out, right? No problem. Now Now, the reality is if it's really cold enough, that the ice is covering everything, it's cold enough that the sun isn't shining anymore, but that's a different problem. So little goes into the ocean, so it's happy, it's stable. Nothing happens to it. Let's suppose the thing pulls apart, like where that polar bear was walking, and so we now have a dark area. So that's gonna suck up some of that energy. Instead of it just bouncing off, it's gonna go in there and warm it up. Diagrammatically, this. So this coming in goes back out. This part though, some goes back out, reflectance off the ocean. Some goes in to warm this up. If I make this ice warmer, what's gonna happen to it? It's gonna shrink it. What's the next step in the operation? Less ice, less reflectance. Less ice, less reflectance, more absorbance, more heat, less ice. Around and around and around, it goes in a circle. We call those feedbacks. Let's call it positive feedback because the effect keeps going. All right? To put some specifics on it. This is a view, satellite, basically a satellite view of the southern hemisphere, Antarctica, the landmass, and this is the very tip of South America. It's a fun place, I won't go into that, but at this point, the white is the sea ice extent as of last week, satellite imagery, and so that's fine. What is also shown on here is over on average from 1981, which is when the satellites first came online, to the year 2010, is just a baseline. That's where the sea ice was. So we look at the area covered and how it evolves over time. In this particular case, sea ice is a little further out here than the average, less so here, less so here, less so here, less so here, and the net's going to be negative. But this is a way to contrast. This is the difference, not in how many square miles, but how much difference there is. And which season is it right now in southern hemisphere? Right now, we're getting ready for winter, right? It doesn't feel like it, but we're easing into the wintertime season. It's been the hot of the day, the sun's day is going to get shorter, there's going to be more energy, less energy, blah, blah, blah. What's going on down here?
Should be getting warmer, maybe getting into spring.
The inverse, it's getting warmer because they're moving into the summer season, because the two polar hemispheres, because of the way the Earth rotates, are seasonally opposed. And so, yeah, the project that I'm working on right here, we go down there in March, which turns out to be sort of in the middle. It's lousy weather there all the time, but there's a time when it's less lousy. So that's just fine. This is one way to represent it with a map. A second way to represent sea ice, oops, what is that slide doing? Okay, so this is the follow-up. This suggests that there's less sea ice, so it breaks up the question, what's going to happen to that? Less sea ice warps when this. Theoretically, you're going to get more warmth. In our simple model, that will work. The real world's a little more complicated than that, but that's the conceptual. The second way that we always look at things is with time series. We plot some property over time. The time series you're most familiar with is the stock market. Stock market, stock values, they're plotted over time. Bounces like a yo-yo. Somebody sneezes, it goes up, or somebody says a chew and it goes down, or whatever. So this is putting some numbers on it. This is the time of the year. This happens to be, well, this is going to be various amounts of sea ice. The gray is the average, and there's a couple statistical parameters because it's not exactly the same and all of that. And then they've identified some years. And so the year 2014 had a lot more sea ice in Antarctica than the average. The golden years, 2021, sort of the same, and then what's happening so-called in 2023. 2023 hasn't played out yet, but there's considerably less sea ice. One could reach the conclusion that there's going to be some sort of feedback increasing this, and that might be okay. The problem is next year it probably might bounce back here. So there's a bouncingness of this sea ice, but the effect can still, the conceptual idea is still the same. Lady with the pink drinky thing, what do you need to know about sea ice that I haven't told you?
I guess how it goes from, like, in 2023, how it would go from down that low to going up higher, like the way the energy is.
So if we think about this a little bit, the sea ice, what I've just, the simple diagram that I've made a box out of is just the incoming solar radiation. The sea ice rests in the ocean. The ocean has its warmth temperature also. And so if it turns out in Antarctica, there's what's called the circumpolar polar current, and we're going to talk about it a little bit more. There's a current, we saw pictures of the storminess before the other day. But basically there's a current that goes around that. So if that water temperature changed for some reason, that could overwhelm just what sunlight's coming on it. So that could change it a lot. And this graph doesn't actually give you a clue why it got shorter this year. Could have been, again, because it was warm water. Or it could have been because there was more sunshine, or the atmosphere. Then when there's also that sea ice is setting with the atmosphere, air temperature. It turns out you have to have an air temperature, to get sea ice, you have to have an air temperature, I think it's about 10 or 12 below Celsius, pretty cold. So, short answer to your question is other things could kick in. And we should be, we always have to be aware. We don't need to memorize every other factor. We need to be appreciative that we shouldn't just try to explain a whole graph of a complex system with one thing. All right, sea ice with time series, we've done that. Formal definition of feedback, so I walked through an example. A formal definition of feedback goes something like, there's a process in which changing one quantity changes a second quantity, and in change in the second quantity in turn changes the first. There's a loop. Loop. Something happens, it kicks around whatever caused that something to happen. It got the sun hiccuped one day, or the sea ice, and so it was a really sunny year, a lot of sun, warmed up a lot of things, warmed up the ocean, melted the sea ice, kicked it in. The controlling factor gets back to this first argument. The lady in the black top. Do you know any other feedbacks? Have you ever seen anything where the sort of comes around in a circle? Anything that you're familiar with from your study, whatever your major, your study area is? So conceptually, this class has a feedback mechanism. You put a homework in and we comment on it. You put a better homework in, we comment in it, and everybody gets happier and better at it. So there's a simplest feedback that we try to employ. There are two kinds of feedbacks, one called positive and one called negative. And it has nothing to do with the way it happens. Positive has a reinforcing feedback, amplifies the change. The ice gets smaller and smaller, and it's amplifies, it gets smaller and smaller. That's a positive feedback, even though the ice is getting smaller. It has nothing to do with the size of the ice. It's the behavior of the system. On the other hand, the thing called the negative feedback acts to balance it or reduce the effect. The thermostat in this room had the temperature adjusted, and then we came in mass, and we've got a bunch of bodies here giving off heat. So what's the thermometer doing? it's doing something, it's sending some signal to this, but is this a negative or positive feedback? As the place warms up, because we have people in here, what's this thing sending a signal to? What's it telling the HVC system to do?
To cool down.
To keep it at the same temperature, even though we've just added quite a bit of heat between the lot of us. But the temperature doesn't get hot here towards the end of the lecture, right? Because a negative feedback that involves this thermostat and the cooling system is designed to keep that regulation in place, and it does. So it's not whether the temperature went up or down, it's whether it stays stable or it takes off. And it could take off by getting hotter or colder, it could take off by, either way, positive or negative. That's the most confusing thing about the terms positive and negative. All right, so we talked about a positive feedback and sort of something that's worthwhile. Anybody else got a positive feedback? An example of a positive feedback? Gentleman in the black shirt.
I was gonna say an exponential curve.
I'm sorry?
An exponential curve.
Okay, an exponential curve tells me about what's happening. Does it tell me the mechanism? Does it tell me the process by which I got that exponential?
I guess not.
An exponential would be a good way to represent a system. The area of the sea ice change might be an exponential curve. It's not quite an exponential curve, but might be, because that reflects the system. It tells me nothing how it happened, right? Yes?
For the business people in here, would supply and demand be an example of a feedback?
Can you elaborate on that?
If the price of something is based on the availability of an item, and the item is desirable, and again, I'm not a business maker, so bear with me here. The feedback.
But you're a good consumer, I know that.
I am a good consumer, I do like to shop, so if an item is limited in supply but the demand increases, could that then generate a process in the system where this item is produced, creating more of said item, dropping the price, and as the price drops, the system rebalances?
What do you think the answer to the question is?
I feel like that's a bit more of a complicated, like there's both a negative and positive, because the price would be.
Might be a little more
decreasing.
complicated than one loop,
Yeah.
absolutely.
One example of a positive feedback loop I hear about a lot in climate is the permafrost melting in Russia, because it's releasing a bunch of methane gas, which will in turn supposedly melt more permafrost, which will release more gas.
And oftentimes the conceptual idea is that's a positive feedback loop. How important it really is, that we argue about a lot. Yeah, sure, methane gas is a greenhouse gas, that should work, but it only lasts so long, so it's a more complicated problem. Back to your recognition, though, that it involves more than one loop. That's actually a key point here. What you talked about with releasing the methane gas from permafrost, that's a positive feedback loop, theoretically, but it has no way to stop it. So should all of the permafrost disappear? Well, it hasn't, because the geologic history, we know that permafrost has not disappeared completely. So for positive feedbacks, as dramatic as they sound, and you get this from the news bites, they have to have some controlling factor, as in Liz's example, to bring them back in line. It may not be the same process, but someplace in the system it has to be in balance, because you haven't gone that far out of balance. The fact that we might take a while to adjust to the balance is a different problem. If we stop, the CO2 levels, they go up wherever they're gonna go, you're gonna get into a balance someplace. Something's gonna kick in. All right, we do not have balance. For example, the hotter Earth, because of the black body, K to the T to the fourth radiates more energy. So the hotter Earth is going to be in balance even though it's hotter. It's not a question of where the temperature is. Balance could be anywhere. And most of the time, we'll get different systems involved. This example had two different, the consumer side and the production side in round numbers. The timescales could falter, so you keep reading about housing, just went nuts, the pricing of housing. Well, that forced people to stop buying housing, so that's gonna crash the housing market for a period of time. It'll come back. The timescale is, somewhat immaterial. Lady way in back, what else do we need to know about feedbacks? I'm sorry, with that, they're tearing that building down behind you down, so I'm gonna sneak up here to get. Example of, what's an example of a positive feedback? Positive is the ones that go out of control, we need an exponential curve. Sea ice was one of them. The other one we're gonna do is the so-called water vapor. That's a big hunt, we're gonna do that again. Another potential positive feedback loop temporarily is sort of the stock market. Somebody buys a stock and they say, oh, it went up in price, and so I'm gonna buy more, and so that brings the demand of that, keeps escalating the price. They typically crash after some period of time because something else happens, but that act of reinforcing itself kept it positive for a period of time. Does that help a little bit? Okay? Yes, sir.
So positive is largely changing the first quantity, which means if the data of the first quantity is, going down, it's also called positive feedback.
No, you can have things go down in sign, in magnitude, and they could make a positive feedback or a negative feedback.
So
The positive and negative are deceptive. It's not the sign of the magnitude change.
I see.
So it's not my bank account balance, or it's not an energy balance, or it's not a stock market balance, or it's not a widget balance. It's which way is it trending.
So if quantity A makes the quantity B going down, and at the same time, the quantity B push the quantity A also, for example, the data from 25 to 24, that's a circulation, that's a feedback. So they are all going down. For the sign, it's also called a positive one. Do I make sense?
Well, I'm not following 100%, but I'm going to answer what I think you're asking. And what I think you're asking is, but how many elements do you have in there? Do you have 2 elements?
Yeah, only 2.
Only 2, okay. And so column them A and B, and A is the one that's.
A means the first quantity, B
Right,
is the
second quantity. Right, and by definition, the top of this definition tells me that whatever happens to B comes back and impacts A, right?
Yep.
So A does its thing and it impacts B, but B comes back and says, hey, I've done whatever you asked, but I'm gonna now regulate you to either go more
Yep.
as a positive, or I'm gonna rein you in if it's a negative feedback. If I flip the wires conceptually on the thermostat, and it's set so that as it heated up, the thermostat called for heat, we'd get pretty uncomfortable in here.
Let's talk privately after class.
I'm sorry?
Let's talk privately after class. Is that okay?
All right, so positive and negative feedback, so we're off to the races. Feedbacks are all over the place in the natural world. This is a small subsampling of the big ones. And so we see things like human population, in terms of population, affluence, and technology. And we see floods, and we see open sea, and we see albedo, and we see sea ice, and polar bears, and penguins, and blah, blah, blah. This is just a small sampling of things, but it's an example of positive feedbacks in green and negative feedbacks in red. This is focused particularly around atmospheric temperature, which you could make up a diagram for ocean temperature or anything else. So the one we just examined was basically sea ice to the open ocean to a property we skipped over a little bit, albedo, to make that loop. That can have a downstream effect on polar bears because they have to swim further, or penguins because there was a mass mortality of penguins in Antarctica a couple weeks ago because they didn't have sea ice. So this is what we just talked about. What I want to talk about next is this atmospheric H2O and atmospheric temperature, that feedback. Green positive. Okay? The other thing about this is this might be positive and this might be positive, but it goes through here, it goes through a couple different steps and it gets back to here somehow. It's kind of fascinating, the positive feedback, watching that crane tear that building down. At any rate, we're in feedback effects. We're going to talk about the atmospheric water vapor one. The water vapor. Water vapor's H2O is a gas, greenhouse gas. And what is the most important greenhouse gas? And the answer is not CO2, it's the one that's got the best publicist, got the best person that writes it in the journals. Water vapor is the unsung hero, he keeps you going here. If water vapor were to increase or decrease, how would that change the temperature in the atmosphere? It being a greenhouse gas, the gentleman in the green shirt, if I increase the water vapors with the greenhouse gas, what's going to happen to the temperature in the atmosphere?
You increase the temperature.
It'll increase, okay? And is that the end of the story?
Probably not.
No, I wouldn't bring it up that way, right? If the temperature goes up, you suggested, I agree with it. What happens to the atmosphere's ability to hold water vapor?
That also increases.
Excuse me?
That also goes up.
The ability of a container of air to hold water as the temperature goes up increases. That's your suggestion. Is absolutely right. You can hold much more water at a higher temperature than you can at a lower temperature. In fact, you can get to the point where low temperatures you can't hold much water vapor at all. It doesn't have to be that cold. I want to examine this a little bit in the next couple of slides. To me, this property was exemplified when I was working in Antarctica, and what we would see is little ice crystals coming out of the air. No clouds in the sky, but little ice crystals. The water vapor that was coming into where we were came into a cold area, it couldn't stay in the atmosphere, so it precipitated out as little delicate ice crystals. Compare that with a good Cincinnati August day where the temperature is high humidity. Okay, so what happens, we'll examine that in the next couple slides, and here's a preview of where we're going. Ouch. How much water vapor could it hold? Now, we're gonna dig into some details here, some nitty-gritty math. We're gonna have another math equation. We're not gonna have to solve it, but we're gonna put it on. It turns out that the relative humidity, which is a measure of how much moisture you can get, is the actual vapor density. And that's gonna be a given number, versus divided by the saturation vapor density versus 100%. Saturation vapor density is a function of temperature. This isn't the formula that we're really gonna get nitty-gritty with this next one. But basically what we're talking about is that there's so many grams of water per unit volume. And the higher that number is, the relative humidity, the more water vapor. In a not quite so simple way. Okay? What controls that saturation point? Well, turns out it's not one thing, it's multiple things. So I'm going to take this opportunity to introduce you to an equation that has a lot of variables. Well, I'll get to the concept first. The concept is this. Here's cold air. Here's the air molecules shown in green. They have a spacing in geometry. Here's warm air. They have basically a similar geometry, but they're further apart. So the water molecules are restricted in the cold air, but they can be more present because the molecules are further apart in the warm air. So it's temperature, it's also how many air particles and how many water particles. Make sense or not? Not so much, okay. What's the pressing question we need to know? Concept is, what's the concept? As it gets hotter, what happens to the amount of water vapor that can be in the air?
Gets lower. Or wait, no, as it gets hotter, like more humidity.
As it gets hotter, you can get more moisture.
Yeah.
So on a cold winter's day, there's not much water vapor.
Is that why it snows?
Excuse me?
Is that why it snows? Is like,
In fact, it has something to do with it, yes. It would snow, so if hypothetically, if you had a day where there was a lot of water vapor in it and cold air came in, it would precipitate out as snow or rain. It's snow, then rain. Okay. Is that your question?
yeah.
All right, gentleman back here has a question.
Could you increase the temperature of the air by increasing the amount of water in here? Like to the inverse, whereas there's more heat, you can have more water. Can you force the heat to, or like the air to accept more water into it?
It's going to be, I'm going to justify it on the next, I snuck ahead to do that. Short answer is yes, but I'm not going to give the full explanation right now. What it would mean is something else had to change that. You couldn't do it simply by that
Right.
property. Okay, and so that's sort of a theme here. We're seeing things that can happen because of A, but then there's B lurking in the background. Anything else on this? All right, now this is another nasty equation, but we don't have to solve it. PV equals nRT. It's a basic equation in thermodynamics. What it really is the air pressure. That's a variable we haven't talked about. Down here at the, close to the Earth, down here at, we're only a few hundred meters above sea level, the pressure is fairly high compared to what it would be on the top of Everest. The volume that you're talking about. So the pressure times the volume or some number. And they are linked via the number of moles, how much you have, times some fudge factor, R, and the temperature. So we've been talking a little bit about temperature and the N and this fudge factor. So we're messing around with that, and then if they are, but in response, we could be messing around with, if we change those, we're gonna mess around with pressure over volume. So we can inject a lot of moisture into the atmosphere. That either means the pressure has to go up or the volume has to go up to compensate. More water, higher temperatures, fine. But the pressure has to go up, or the volume, or both. Volume and pressure are related algebraically, as is basically how much water, the N, fudge factor, and temperature. Fudge factors to keep the units all right. Why I'm introducing this is we can turn 4 different knobs. We can take any one of those variables and change the equation. So I want to show you how nasty that can get to think about. And the way that we think about it is something called this chart. And this chart is actually a very useful thing for one industry, or several industries. But typically we see graphs of 2 variables. We just talked about 4. So how do we represent 4 variables? I don't have, I'm going to show you an example just to you appreciate that this multiple relationships gets to a mess. Typically though, we want the x-axis to be the temperature, and then we show the other properties in some vertical axis or some other way. The reason that we do this, if you go to mechanics studies or whatever it's called, they're used to design air conditioning systems. You can maintain a certain comfort level, not with just temperature, but the humidity. You've been in the same temperature with a high humidity versus a low humidity. Your self-regulating temperature system is called sweat, perspiration, evaporation. If you can't get rid of that evaporation, you can't get cold. So the people who design these systems don't talk just about the temperature, they talk about the humidity. And it turns out people are only comfortable in a certain range of temperatures and humidities. And then we could ask what the girl that wants to design a HV system is, how much energy would it take to do this? Because I want to get a system that's optimized to keep people comfortable, but I want to do it with less energy, obviously. So this can be worked really well in this example. It doesn't necessarily scale very well to the whole globe because there's so many other things kicking around. Just worrying about the environment of this room and this building, easy. The environment of the globe, not so much. I'm just saying here's a nasty graph that if you want to design one of these, you'd have to understand. Temperature. This is humidity, relatively speaking. But all of these other curves, the red lines and the green line and the dotted blues are those other variables on that equation. And so it turns out that on this whole graph, people, you and I, are only comfortable sort of in this range of temperatures and this range of humidities. Fine. In the past, we've tried to appreciate this by graphing it, but we're giving up on that for this year. Who needs to know something about this graph? Besides, how much longer is it going to stay up there? Move it off. The lady that next to the pink cup. What more do you need to know about this graph or the concept of humidity and temperature?
What's the red dot?
The red dot, I think, is a misplace. I think I started out doing something with the red dot and said, how do we get there? I think I had this set up as an exercise. And so the real answer to the question is, if you started here, you want to get to this, what do you have to tweak? Well, you could tweak this, the green one, or you could tweak the red one, or you could tweak the blue one. So that's the kind of, not only do we get where we want to be, but we have to start someplace else. So you can, how do you do that? And is it less expensive to tweak the green or the red or the green? That's what the engineers would ask. And I don't know the answer to that. I mean, I could figure it out. I could sit down and tinker with it, but I don't know it off the top of my head. Okay, let's dispense with those. Let's go back to the climate sensitivity for a moment to finish this up. Water vapor is still a greenhouse gas. Time are we at?
It's 3 o'clock, 2:57.
3 o'clock, so we need to be out of here in 15 minutes or less, right? Preferably less? Preferably, yeah, okay. Involved in some kind of a feedback. In some kind of feedback, and hence the energy balance system. Oh, what are all those white things in the sky? They're water vapor that's cool enough that you can see them. They're clouds. Clouds control how much sun goes through them. So not only is water vapor a greenhouse gas and acts invisibly, The visible part of clouds turns out to be quite gnarly, because it depends on how high they are and how light they are. And so could it be that simply something like water vapor, because it has different manifestations in the cluster system, could be a reason that the climate sensitivity didn't come out very well? Yes, it could be. Was it? Not necessarily. But the point being that our climate sensitivity is really just trying to get us to focus on one problem, one variable, CO2. I think that's a mistake. I think it's much more appreciative to understand that there's a whole bunch of things going on. Not in excruciating detail, but that they're linked. So I would submit that water vapor, because it's a greenhouse gas, it has the positive feedback loop of the humidity itself, the moisture content. It has both positive and negative feedback loops in the cloud phase. So water vapor in itself doesn't always, and we know, why am I doing this? Because we know that it's sometimes the atmospheric plane, that areas are much drier and other times they're wetter. And this sort of sets up the next module, basically. All right, we're winding down for follow-up. Clouds, water vapor, aerosols theory, we don't need to worry about those too much. So there's uncertainty and there's unsettling here. Let's get on to deliverable. This is more interpretation, this is more analysis, this is more thinking. There's not a right or wrong answer. We jack up the points to make it worth our while. The concept is to synthesize this stuff. One of the questions, number 4, might require you, or probably will likely require you to get some information from the internet. Do that. Just be sure to cite your links. We're looking for answers in the 3 to 5 sentence range. A lot of the comments I made was you could improve this answer by giving a little more depth, a little more arguments. We're going to ask us to practice that a little bit. 3 to 5. You're not going to write a long paper about this, but 3 to 5 shows me you know what you're doing or not. We're going to evaluate it based on displaying an understanding of the concepts and how well you employ them to the particular problem. So this is a little more subjective. This is where it'll get a little uncomfortable with some of the problems we're going to ask, but because there's no answers. All right, so let's be sure that everybody's got the questions. Why bother with climate sensitivity? It's sort of a way to summarize what we did with climate sensitivity. Number 2, let's be sure we know what a positive feedback is. Pick your, yes sir?
On there it says red arrows is positive, green arrows is negative.
Did I get it backwards?
I think you might. The key on the slide says the other way around. Just wanted to.
Okay, so should we pay attention to what I say or what do you think?
Well.
Yeah, see, bruh. But if you're consistent in the interpretation, it wouldn't matter. So then you might say, for positive feedback, blah, blah, blah. And then it would be clear which it is, whether it was the right arrow or the wrong arrow. And as an exercise, you're going to have to figure out how to make one of them work. Geez, I double checked it too.
I don't know, you want to see my
No, I
say?
All right, so positive and negative feedback. Figure out, look at the arrows and figure out which one interests you and go into it a little deeper. So that's 2 and 3. So far, so good. This is the concept of nonlinear. I started with a big tirades on the first day about nonlinear systems. Everything that we've talked about now with those simple equations are linear. Take it one level of abstraction. If I push it, I push it, I push it, nothing happens. I keep pushing it, it breaks completely. That's a nonlinear system. We are sold on the notion that the climate system is a linear system and it only depends on CO2, and that's hogwash. CO2's in there, it's not the only thing. So let's see about examples of other nonlinear systems. There's hundreds of them. All right, then the real thinking question, hypothetically. You're a city planner for wherever your hometown is. Oh, so you can tell me where your hometown is, that's fine. And now you're in charge. One project that's going on is a new housing for the elderly. So how would you advise the engineers that are gonna do the nuts and bolts of the calculations to deal with future temperature predictions if the future temperature predictions depend on that climate sensitivity? What I'm looking for is how you advise them. In other words, take it to an express. You don't have to do the calculations. You might as well do the calculations. But just what's your advice to the people who have to do the calculations? So they assume this temperature difference, and therefore we assume what the CO2s are, therefore we assume the temperature? Is that the best way to proceed? It's a model. It might be the model you choose. Another model might be to say, well, maybe the sensitivity is not the best estimator of the thing, so we need to deal with more worst-case examples. And the engineer's gonna say, that's great, but it's more expensive. Which do you want me to do? This is a fundamental question. Questions, problems or designs or plans to do things that you don't know what's going on are always more resource intensive than if you really know what's going on. Or think you do at least. Questions on the questions on the questions. Do we get in under the time limit? Close enough. Liz has a question.
On slide 16 with the flow chart
Today?
today, yes. Are there any terms
Are you gonna get me on the red and green arrows again?
No.
Just to prove that.
But they do mention a lot of topics. Are there any topics up there that y'all would like defined, or would you like us to point you in a direction so you can read up on them?
Right, you're welcome to pick any of them to describe.
For example, we mentioned albedo a lot. Does everyone know what albedo is?
Albedo.
Albedo, sorry, albedo.
It's a reflectivity measured in the ratio of 1 to 0, how much energy is bounced off the surface, off a surface.
Basically, it's how much the light kicks, how much the ice kicks light off the surface.
How much
Is there anything
inspiration.
else up there that needs defined, that maybe?
I don't know, does anybody have something they want to get into but they're not sure where to go? This one could be pretty popular these days. This is the one the gentleman talked about, droughts we'll get into. Evaporation, hey, you don't want to get into that. Humans are in this thick of it. I'd pick one a little simpler than humans myself, but that's up to you. All right, so this is all due on Thursday. We're almost ready, we're almost seamless on our technical glitches and we should be okay, but please ask us if something doesn't make sense or we have some glitch that we haven't seen. I'll see you on Thursday.